What I want to do in chapter 7 is I want to talk a little bit about, there's really only one or two big ideas in chapter 7. I'm not going to go into as much detail as the book does, but the idea is suppose that you have some sort of a sample, which I'll call S. So say we just have the sample 1, 4, 5, and 8. And we could do all sorts of things with this sample. You could use R to calculate the mean. And so if you typed in x equals c 1, 4, 5, 8 and stored the data, you could figure out that the mean is 4.5. So this is the sample mean, so that would be 4.5. And the sample standard deviation turns out to be 2.8868. 2.8868. Okay. And so what we're going to do in chapter 7 is we're going to talk about not just the sample itself, but we're going to think about properties that the sample has. And in fact, we're going to take samples of the sample. And so what we're going to do is we're going to start with, let's take samples of size n. Okay, here I'm going to just pick n equals 2, so I'm just going to pick samples of size 2, in other words, pairs of elements of S. But in general, you can do this with samples of whatever particular size. There's some nice R code that's built into this, which I'll show you in a second. So we're going to take samples of size n. In this case, our n will be 2. And so what we're going to do is we're going to look at those kind of subsamples. And there's going to be 6 of them, because that's 4 choose 2. We have 4 things. And we want to choose 2 of them. There's 6 ways to do that, it turns out. So we could look at the sample that's 1 and 4. We could look at the sample that's 1 and 5. 1 and 8, 4 and 5, did I miss one? 1 and 4, 4 and 5, 4 and 5, oh yeah, 4 and 5 and 4 and 8, and 5 and 8. Okay, so there's our 6 samples. And then what I want to do is I want to think about, given these samples, what's the mean? What's the mean of the samples? And so we can just calculate this by hand. So this is samples of size 2, and then the mean of those samples. So the first sample would have mean 2.5, and then 3, and then 1 plus 8 is 9. So divided by 2 would be 4.5, 4.5, 6, and then 6.5. Okay, so those are the means. And this is actually the set that we're going to study in this chapter. So for whatever value of n you want, it doesn't matter. We're going to study the means of the sample means. So we're going to study what is the mean of that set, what is the standard deviation of this set. So we're going to think of this kind of as a new set. Let's call it S sub mu. So this is going to be 2.5, 3, 4.5, 4.5, 6, and 6.5. Okay, so that's going to be our new set. This is the set of all the means. And it turns out that if we look at the mean of all the means, in other words, pretend that this set 2.5, 3, 4.5, 4.5, 6, and 6.5 is your new sample. So suppose that's the case. What's the mean of that sample? So what I'm trying to say is if we take 2.5 plus 3 plus 4.5, 4.5, 6, and 6.5, and then divide by, we have 6 items there, it turns out what we would get would be the mean of the original data set, which is 4.5. So it turns out that we're always going to get that 4.5 value there. Okay, and likewise, the standard deviation that we would get, so I'm going to call this S, and I'm mixing up my notation here. I need to fix this. Sorry, I want the mean of the samples. That's our notation. Okay, I had that backwards for some strange reason, but then the standard deviation of the samples. And it turns out if we take the standard deviation of the samples, what we get here won't match up with what's predicted, but what's predicted is that you get the standard deviation divided by the square root of n, where n is the size of your sample. Now, this is a really good approximation when n is large. So the larger n is, the better approximation we're going to get here. But the larger n is, the harder this is to do, right? So if you have 100 data points and you want to talk about how many samples of size 50, there's a huge amount of those, although this is a better predictor of what that standard deviation is going to be. So this is really the only thing that we need to know here, is that the means of the samples, so let me just put a little summary here. The means of the samples are going to themselves have a mean, and this mean is always going to be the mean of the original data set itself, and the standard deviation of the samples is always going to be approximately equal to the standard deviation of the original set divided by square root of n. Okay, the first one is always equal to, that's an equality. The second one is approximately equal to. I'm going to write them both as equals. There's a theorem that's kind of hidden here called the central limit theorem. You know what the central limit theorem says is that start with any sample that you want. It doesn't matter if the sample comes from a normal distribution, a binomial distribution, a uniform distribution, if it's not uniform at all, if it's, it doesn't really matter what the sample is. But the idea is that sufficiently large sets S have a sample mean, so they're going to have a sample mean mu sub x and a sample standard deviation that is normally distributed. So that's normally distributed with mean mu. So with mean mu in standard deviation sigma over square root of n. In other words, what this is saying is pick whatever set you want. I don't care what the set is, make it whatever you want. Do this game where you find the means of the different samples. It turns out that no matter what the underlying set is, the means of the samples will be normally distributed. Okay, so no matter what set you start with, they'll be normally distributed. Okay, and maybe in the next video I'll do some graphical examples of this. Okay, also in the next video we'll go over the R commands for this. Okay, but this is the central limit theorem.